Today we are looking at our functions unit, and we can fill in and update our table of contents, also update your page numbers. We're going to start with our discrete and continuous data notes. Data can be collected in a few different ways. Qualitative is like the quality of it. Like you ask, hey, how was that movie? And you respond like good, or it was bad, or it was terrible, or it was awesome. Those are words that we use to describe things and their quality. We're not really going to talk about that data today. We're going to talk about quantitative data, which is numbers of some kind, so our quantity of our numbers. And we have two different types of those, and we need to know the difference between the two. We have discrete data, which is like this here, we're counting. And then we have our continuous data right there, where it continues throughout the whole thing. So let's look at what that is. Discrete functions have distinct and separate values that have no connection to each other. So think about counting things. Like if you were to count students in the classroom, you can't have a half of a student. I also like to think about like if you buy something, right? You can't buy 3/4 of a hat. You can either buy the whole hat or no hat at all. You could buy 2 hats. You could buy 5 hats. You can't buy like 2.5 hats. That's not a thing. Another example is like rolling dice. You only have those whole numbers in there. You don't have any halves or fractions or decimals, so they're distinct values. Continuous functions can take on any value within a certain interval. So each value is connected to the next. Like if you're measuring something, like a person's height can be measured, and you will hit every single fraction and decimal on your way up. Time in a race, we can get into fractions of seconds, right? And a few extra. Yeah. So why do we care? That's a great question. So we can appropriately represent numbers. We've talked about here where sometimes we put the dots and we want to connect them, and sometimes we don't connect them, sometimes we do. We want to make sure it's appropriate. So when you're given a real-world situation, you need to decide on an appropriately domain, which is our x values, and range, which is our y values. All right, so we need to see if they're discrete or continuous before continuing. For example, if I'm counting the number of people in the room, I would only need whole numbers. 0, 1, 2, 3, 4, 5, 6, right? This would be discrete. That would be an example of a discrete domain. And then, for example, if one year you are 3 feet tall and the next you are 4 feet tall, it would be appropriate to assume that at one point you were 3.5 feet tall. You don't just jump overnight. You do grow. Even if sometimes you seem to get taller overnight, you still at one point overnight were that measurement. So between 3 feet and 4 feet. So it looks like this. So this would be an example of a continuous set of data. And usually we have inequalities here. We got commas there. Beautiful. Next. All right, let's start with describing the domain and range. So our domain is, and we need our little braces here. Okay. So our domain, we want all the numbers on our x-axis from 0 to 6. So if we want all of our numbers from 0 to 6 and they stop, we want 0 less than or equal to x less than or equal to 6. How do we know we were from 0 to 6? Well, we're looking at our x-axis, right? Because domain is our x coordinates. So we started here at 0, way up here, and we continued to our numbers greater than that. And we kept going and going and going and going and going until we hit this 6 here. So we want all the numbers from 0 to 6 on our number line. So we write that as a compound inequality. The next thing we need to look for is our range, which is our y values, which is going to look very similar. So we have the set of all numbers, If we look vertically here, we're still starting at 0 and we're going up to 6. So it's going to be the same thing. The only difference, since it's our range values, we're looking at our y values are also between 0 and 6. So we have our domain, we have our range. Is the domain discrete or continuous? Well, obviously you can see there's less than or equal signs there. Let's just circle it. Let's do that. It's continuous. You can write it out in words if you would like, or you can circle it, your choice. But that one is continuous. Now notice it just asked for the domain. It did not ask for the range. So we're looking at this one right here. All right, next one, our domain is, now notice we do not have those lines anymore. We have distinct data. So we have an x-coordinate at 0. We have an x-coordinate 1 up here, 2, 3, 4, 5, and 6. So we are listing out 0, 1, 2. There's our domain. Ooh, watch out for your braces. Make sure you've been practicing those. It's better. It's not great. It's better. So make sure you're practicing those. Our range. Ooh. Is all of our y values. So again, we have a point on our y-axis at 0, 1, 2, 3, 4, 5, and 6 as well. So it's the same. Oop, that's a comma. And then it asked again, is the domain discrete or continuous? Well, since we have commas and we have very distinct data, it is discrete. You can write it, you can circle it, whatever you want. All right, here we go. Keep going here. Describe the domain. All right, so our domain here, remember it's our x values. So if we're looking at our x-axis here, left to right here, we actually start at 0 and we keep going. There's no end point. That's everything bigger than that. So actually, I'd want to write our x is greater than or equal to 0. How do I know it was or equal to? That dot right there is solid. It's on the 0 line. All of our numbers on our x-axis are greater than or equal to 0. And then if we want our range, that one is a little bit different too. We're looking at our y values, but we actually start at, if we're going on our y-axis, we have nothing here, nothing at 0, nothing at 1. We start at 2, and we want all of our numbers, for y greater than or equal to 2. Ta-da! Then we want to know, is the domain discrete or continuous? Well, it does have an endpoint, but it's continuous. We're hitting all those fractions and decimals between it. So even though it doesn't continue in both directions, that's okay. From a table. This one's a little bit trickier. We have to think of the context. You could graph it if that helps you, but I like to think about it. So we'll think about it here. If we're talking about bags is our input. And again, we're still asking, is our domain discrete or continuous? So we're asking just right here about our input of bags of marbles. Well, it sounds like you're at a store and you're going to buy a bag of marbles. Can you buy a half bag of marbles? No. Can you buy a 1/16 of a bag of marbles? No. So it's not continuous, it's discrete. That is a discrete domain. And you can write that if you would like to in your notes, that you can't buy a fourth a bag of marbles, if that helps you. Here we go. We're talking about, read our titles here. Is the domain discrete or continuous? If we're talking about the height of a tree growing over years, 2 years, we're going to have halves of years. At some point, we're going to be in August, we'll be in December, we'll be in March. I went way out of order, but still, and even within those months, we still have days, which are like pieces of months, I guess. So this one is continuous. It keeps going and going. It's like measuring things, like with distance of your height of a tree with feet or the amount of years. All right, now this one, we're going back to domain. If our input is within inches, we're talking about a measurement. which I would then claim if we're talking about measurements, if we go back to our definition, we're talking about a continuous set of data points because we can measure and be at any point. Now, I could see an argument for discrete here. We can discuss it in class if you would like, because there's just not quite a full enough amount of information, but with the little information we have, continuous. All right, domain, discrete, or continuous. Okay, so we're domain, our x, our input, hats. Can you buy half a hat? No. Be careful, these are decimals, but they're asking is the domain discrete or continuous? And it is, in fact, discrete, not continuous. All right, we can start the next one here. So those are those first 2 pages to glue in. We're on the second set of pages here, understanding linear functions. Mathematics attempts to model what is observed in the real world. So we start by counting objects, like we have been doing since elementary school, counting 1, 2. We move on to representing objects with variables, like we've been doing in middle school so far. We're getting to the point where we now write equations that represent relationships between variables. So Algebra 1, we focus on 3 major functions, linear, exponential, and quadratic. In our integrated class, we will be focusing on just linear. We will mention exponential, we will mention quadratic, but we won't go into them in depth until next year. So our job as mathematicians is to identify the change and use the appropriate equation to attempt to model it. In the next few units, we will learn about linear functions that are both continuous and non-continuous. As you can see, we have one of those piecewise functions I mentioned in one of the classes yesterday. We have 3 forms of a linear equation. We have slope-intercept, standard, and point-slope form. We're going to focus for this unit with either slope-intercept form or standard form. How can you identify linear equations? You can prove that an equation is linear by rewriting a given equation in standard form. So standard form is ax plus by is equal to c. This is something to memorize, hence why you see the golden star up there. A and B are picky. If we look through here, A, B, and C are all integers. They can be positive or negative, but the idea is that they're whole numbers. A, B, and C are not fractions. They're not decimals. They're integers, which means they can be negative numbers, positive numbers, or 0. So no fractions. A has to be positive. That's tricky. And we can do things to make sure it's positive. That's fine. Then our final thing is we can factor out a greatest common factor. So the greatest common factor between A, B, and C is 1. So if we factor everything else out and we get 1 and done, good to go. We'll look at a few examples of these. So it's always helpful to write ax plus by is equal to c. That way we know that's what we want it to look like. Our y is already over there on the left. All we have to do is get our x term over there. So we're just going to have to add 3x to both sides. That way we are left with, now notice, we're not going to put the y first. We're going to put the 3x first plus y equals 4. Is that in standard form? Well, yeah. A is positive. A, B, and C are all integers, right? 3, 1, and 4, good to go. There's no common factors between them, so yes, it is linear. Is it linear? Yes. If we look, we can see that this equation, in fact, is linear. It makes a line. So you can always check on Desmos and type it in to see if it makes a line. So this one, is it linear? Well, the tough part here is that we need to get it into our ax plus by is equal to c. Now, if we divide by y to get the y out of there, the 6x will then have a y and the 4 will have a y, but the y will be gone. So we can't divide the y. We can't divide by x. We could factor out the x, but that wouldn't work either. This one, I don't think we can do. We can't get that. Since we have two variables, and since there are two variables, it'll make our graph look different. We can check it on Desmos just to be sure, and we can see that that is not a line. Our goal is to get it into ax plus by is equal to c format. Well, 4 is over there, good to go. We do have a y here, but that's not 7/1. If we're dividing by y, that would be like b over y and a over x. That's not quite going to work. If we multiply everything by those, we're going to end up with an x here and an x here, and then a y here and a y here. So it's going to be all funky with our stuff. Oh, no, we're not going to be able to get that into our format. And if we check on Desmos, oh man, look, it looks very similar to that last one with weird looking lines. But it's not linear. It's not one line that's continuous. All right, let's check our next one here. Our goal is to get it into ax plus by equals c. We do have a y. We could subtract x squared from both sides. Whoa. But then we'd end up with a negative x squared plus y is equal to 4. We could get rid of the negative and divide everything by a -1, which would leave us with x squared minus y is equal to -4. But that squared isn't here in this formula. We don't have, it's not going to work. It's not in there. So this one's a no. We could get closer than those other two, but that's not going to work. Let's see what that looks like. Oh, look. That would be a parabola, a negative quadratic. So that is a quadratic function, not linear. How to identify the domain and range of a function. You know this vocab. I'm throwing it at you again. Here we go. So domain is our x values. So we look at the x-axis and ask how far left and how far right the function goes. So what is our x values? So make sure you're looking at your x-axis. Our range is our y values. So look at the y-axis and ask yourself how far it goes up, how far it goes down. So you can use a piece of paper to drag it across the graph. That helps, and we'll practice in class if you would like to. What I mean by that? If we're looking for an x-intercept, that is the point that lies on the x-axis. And it always has a value for x, and then y is 0. That's our x-intercept. So this point on the x-axis, we have a few other words for them. These are also called roots. They're also called solutions. They're also called zeros of a function. Because look, it has a 0 in it. Got a lot of vocab words for some of the same stuff here. A y-intercept is just like an x-intercept, but this time the 0 is in the x spot, and we have a value for y, and it's located on our y-axis on our graph. Just the 0 of a function, and they're only asking for one. They're asking for the x-intercept. For that number where we have a number for x and 0 as our y. We find where y is 0, and then our x is the answer. From a graph, you find where the function crosses the x-axis. From an equation, you evaluate the function for y is equal to 0. So we substitute in 0 for y and solve for x, kind of like we've been practicing with our function notation. So let's practice zeros from a table. Well, look, I got one here. Y is 0, x is a value. This is not the x-intercept, it's the y-intercept. So remember, if they just want a 0, singular, we're looking for the x or the x-intercept or the one where we have a value for x and y is 0. So the next one, not here. We want a value for x, y is 0. Oh, look, right there. Now the final one's a bit tricky. We have to then use our patterns to find where our table would have a 0. See, how do we get from 12 to 9? Well, we subtract 3. So we're going to subtract 3, right? So we keep with that pattern. 6 minus 3 gives us 3. Yep. So 3 minus 3 gives us 0. Okay, cool. And then we have 8 minus 2 is 6. 6 minus 2 is 4. 4 minus 2 is 2. So all we have to do is 2 minus 2, which gives us 0. Oh, look. There it is. Our x-intercept happens to be at our origin, 0, 0. If we find the 0 from a graph, we're looking for our x-coordinate. All right, here comes the happies. Boop. So since this crosses the x-axis at -3, our 0 of this graph, and usually ordered pairs are good. Oops. We have -3, 0 is our ordered pair, which is usually a good way to write it. Sometimes it'll just ask for the -3. That's fine too. But that's where it crosses our x-axis. Notice here it doesn't cross the x-axis. So this one doesn't have zeros. So I'm going to put NA, not applicable. Our graph doesn't go that low, so we don't have any zeros. It would also, you could write no solution or no 0. It does have a y-intercept though, so does this one, but we're asking for the x-intercept. How do you find 0 from an equation? Just a 0. So if we're looking for our x-coordinate, right, our x-intercept, when our ordered pair is x, 0, that means y is 0. So all we have to do is plug in 0 for y for each of these and solve. So if we plug in 0 here, equals 9x minus 4, all we have to do is solve. We can add 4 to both sides, which gives us 4 equals 9x, and we can divide both sides by 9, whoa, which leaves us with x equals 4/9. If you divide that, make sure to put the repeating bar over the 4/10 to write it appropriately. For this one, we'd have our 3x, because again, we want to find our value for x. So we plug in 0 for y and solve. What's nice is 7 times 0 is 0. We don't need to put 0 because anything plus 0 is itself. 3x plus 0 is still 3x, right? So then we can just divide by 3, which leaves us with x equals 5/3. Okay, cool. And same thing here. We have our 2x plus 6 times 0. Whoa. 6 times 0 is 0. Again, that whole term cancels out and is gone because 2x plus 0 is still 2x. Ooh, we can divide by 2. Ooh, that leaves us with a beautiful 6. So if you had to write them as ordered pairs, it would be 4/9, 0, 5/3, 0, and 6, 0. How to interpret intercepts. What do they mean in the real world? We talked about those a little bit ago. We write those coordinates, add those labels, and write a complete sentence. This is review. So if we're finding our x and y intercepts, we look for zeros. So this first one here, we have a 0 and 10,080. So for that 0, 10,080, and we are interpreting that, the pool starts with 10,080 gallons of water. There, we don't need anything more because that starts with implies the 0 hours, right? And then our other ordered pair would be our 14. 0. That's our x-intercept since we have a value for x. After 14 hours, the pool drains completely. You put drains to 0 gallons of water. That's fine. We're talking about our domain and our range. We put those values in there. So here we have our championship rodeo. And children 12 and under are $15, right? So X would be children, as we read here, represents the number of children. X, good. And adults, Y, right? $30 per adult who can attend the rodeo for $180. We're going to use the X and Y intercepts to graph the equation and then describe what the values mean. We could plug in 0 for X and solve for Y to find our Y-intercept. Plug in 0 for Y, solve for X. There's our X-intercept. What do they mean? Well, if we're asking what they mean, we're talking about it in real life. So the X-intercept, if we plug in 0 for Y and solve for X, that means we are not looking at any adults going, only children. So we'd have 12 children that can attend for $180 if we had no adult supervision. Sounds like a bad idea. Our y-intercept would mean if they didn't invite any children, how many adults could go? So 0 children going, we could afford 6 adults to attend for $180. So that's substituting them in and solving for the other one. The descent of an eagle, and you can almost kind of see that that's how the eagle starts, and it's going lower and lower and lower as it's descending. If we look at this as our time in seconds, so that's a quick descent, and this is our height in feet. If we're looking at the intercepts, our y-intercept is over here at 20. So if our y-intercept is at 20, we have 0 for x, and y-intercept is at 20. We're talking about 0 is the time. The eagle started at how many feet? 20 feet off the ground. Our time in seconds, if we're looking for our y-intercept, we already found it. Now if we're going for our x-intercept, our x-intercept would have a value for x, and y would be 0. After how many seconds? 6 seconds. Eagle is on the ground. So it dove all the way to the ground. That's where it's going. Which is the best estimate for 0 of the linear function represented in the table? So we're estimating what 0 would be. Oh, for the 0. Okay, so if we're going for the 0, it's not the 0, 5. That's a y-intercept. When they ask for 0, they want the x-intercept. So we want a value for x, and y is 0. And if we look, it's going in order, but 0 for y would be somewhere between here. So if we're looking, if 0 is our y, x would have to be between 2 and 3. So these are good check-in questions. If you can answer them all, you should be good to go. If not, let me know which ones you are struggling with in class tomorrow. A solution is a value or values, when substituted in, yield true mathematical statements. So our idea is when we substitute in numbers, they make a true statement. So what does a solution look like here? Well, that one's pretty easy. We know that we can subtract 5 from both sides to find a solution of x is equal to 3, right? So when we substitute in 3 plus 5 is equal to 8. Is that true? Well, yes. 8 is equal to 8. Yeah. So it's true. How about here? And this one, it's not just one true number. There are pairs of numbers that are correct, like ordered pairs. So any ordered pair on our line is a solution. So we're going to have a lot of combinations that could work here, right? Like 5 and 5 and 4 and 6 and 0 and 10, right? So if I said, if a solution of the equation a plus 4b equals 29 is 5b, find the value of b. Well, we can substitute things in here. We know this is b, which means this has to be a. So we would plug in 5 plus 4b. We still don't know what b is. That's what we're trying to figure out, is equal to 29. And then we solve that, right? So we could subtract 5 from both sides, which would leave us with 4b is equal to 24, where b is equal to 6. So we could figure out what b is if we need to. If we were to find 3 solutions to this equation, right, we know our exponents now, we could find a lot, right? So if we substitute in, we pick an input, right? Pick any x value. We pick 2 squared. We can figure out what our y is easy. What is 2 times 2? Well, that's 4. All right, so there's one pair of solutions. We could also pick another number. We could pick 3, and we know that 3 squared is 9, right? We could even pick 9 for our input, and 9 squared would be 81. We could pick any input. We could do decimals and fractions, but pick easy ones too. Another way to phrase the solution is satisfies the equation. So you may hear that too. This is just notation. So a set is a collection of things, usually numbers in math class. So for example, our set of numbers is 5, 7, and 11. We have commas, we have the braces. But we can also build a set by describing what is in it. So this is another example of what it could look like, right? So we have the set of, there's our braces, all x values such that x is greater than 0. Now I learned it as the set of all x values when x is greater than 0. So I learned this line as when such that, same idea. That's how we can read it out loud. So in other words, any value greater than 0, right? So in other words, this is kind of the simplified form of it, right? Any number greater than 0. Oop, I did not erase it. So it's just a placeholder there. You can also have a colon instead of the line. So how do we represent solutions? Well, in a set, right, all the numbers for x, where we have are such that we have -4, 1, and 3. We could just write it out as a set. In a one-dimensional graph, if we were to graph this here, right, there's our discrete function. If we are to graph a continuous, we'd have a line on our number line there. If it's a two-dimensional graph, we have a line that could go at any angle, and it continues on forever and ever. In a three-dimensional graph, we can get some crazy things going on, right? We're talking about the z-coordinate just for a minute, right? We can have something like this. Ooh, fun stuff. We're not there yet. So we're going to stick to linear equations. We're going to stick to lines first before we get to any shapes like that. So in order to graph at this point, we can make a table like we've been doing. We did like a few already. We choose x values. We pick them. Pick easy ones. Pick ones that are on the graph. And then we evaluate to find the y. Then we graph those points. So technically you only need 2 points. However, you should always have at least 3 for accuracy. And I always suggest a negative, a positive, and 0. A lattice point is a point at the intersection of 2 or more grid lines in a point lattice. So that's where the lines cross. So we got a bunch of lattice, if our line goes there. So if we would graph this function here, we would pick x and y values. So our x value, right, we could pick a -3, shall we? So if we substitute in the -3 here, so we'd have -3 minus y is equal to 3. So we can add 3 to both sides. We get -y is equal to 6, and then we divide by a negative, so y is equal to -6. And then we graph it. So we go over to -3,
down to -6, and we graph a lattice point. Okay, so I'm getting a little far down. I'll go for 0 next. So then if we plug in 0, we would get a few different things here. If we were to plug in 0, 0 minus y, well, we could subtract 0, really, but we don't need to do that. We would end up with a negative y is equal to 3, which just gives us y is equal to 3. Okay. So our next lattice point would be at 0, 3. Oh, sorry, 0, -3. My bad. I forgot the negative one over there. And since I'm sticking with a 3 field, I'd put a whole number 3. So let's try it with a whole number 3. Let's try with 3. Okay, so if we have 3 minus 0, we could subtract 3 from both sides. 3 minus 3 is 0. So we'd end up with 3, 0. Sweet. And you can start to see the line forming. From there, we can take a piece of paper to line it up and to graph those lattice points so beautifully. Make yours look prettier than mine. And don't forget arrows at the end. So that's pretty much how we do this. We pick values, substitute them in. You can always check using Desmos to see if you're correct. So you just type in the equation x minus y equals to 3. It will graph it for you and show you the line. But make sure you can pick numbers and substitute them in. So I'm going to have you try those last two. And there's our notes.